a minute and then you can take it away.
If you, hey everybody, welcome back to the Colloquium series. And it's our great pleasure to have Dr. Jamie Tayar with us from University of Florida. He got her PhD in 2018 from Ohio State University, and then took a Hubble Fellowship, and she took that to the Institute of Astronomy at the University of Hawaii. A great place for doing astronomy, and she's currently since 2022 been an assistant professor at the University of Florida. So it's all about stars today, and I'll let you get to the specifics, Dr. Tayar. Thank you so much for coming, and we will feel free to jump in with questions at any time. Generally, we're like super polite and inhibited, so we probably won't, but you're totally welcome to. And that goes for the people on Zoom as well. If you've got questions, we can't really see your chat pop up, so just do it with audio and jump in. So take it away, Dr. Tayar.
Yeah, thank you all so much for having me. And as you said, it would be great if you could speak up rather than putting it in the chat, because I struggle to monitor all the things at the same time. So I'm excited to talk to you today about stellar ages and really how well we can know stellar ages, because I think it's something that kind of fundamentally hits almost every field of astronomy. So if you're coming from more of a galaxies perspective, right, you want to understand lots of big questions about the history of galaxies. How do galaxies interact with their black holes? Why are they so large so early on in the universe? And like, what kind of stars are exploding in your galaxy? How are they enriching the chemistry? How is that evolving over time? And for a lot of those questions, you want to know the detailed history of the galaxy. You want to know what it is made of. So that's like its chemical composition, where everything is, the morphology, the dynamics, how everything is moving. And then you want to know when the stars formed, right? Like when each piece came to be. You can help put everything back into a detailed story of how that galaxy formed and evolved. And like, if you think about galaxies the way you learned them in class, right? You learned about, red galaxies tended to have a lot of older stars, lower mass stars, red and dead, not a lot of star formation, older populations. Whereas blue spiral galaxies tended to have like, lots of young stars, star formation, things like that. And so even just looking at a picture of a galaxy, you get some information about the age history and the age evolution. And similarly, if you take a spectrum of a galaxy, it seems like you could learn so much more, right? You not only have just, is it red, is it blue? You have this light split into a variety of different wavelengths. You can see absorption and emission features from a variety of different elements, which tells you something about the chemical composition. You can figure out how blue or how red or what the different kind of combined populations of stars are putting out light. But at that point, you sort of struggle to figure out how you're going to put that all together into a detailed age history for a galaxy. Like, how do you actually extract that from something like a spectrum of the whole galaxy? And so, you have some information about the colors, you have some information about whether there are very young stars or aren't very young stars, but that's not the same as a detailed star formation history. And if you're trying to answer really detailed questions about the history of that galaxy, you want more than it is old, or it is young, or there are some middling age stars. How do you measure a precise and an accurate age? And how precise and how accurate can you go? And similarly, if you're coming from like an exoplanet's context, right, all of the exoplanetary properties are measured relative to their stars. So if you're thinking about the history of planetary systems, which ones are habitable, for how long, what do their atmospheres look like, how big are those planets, are they like Earth, are they like Venus, are they like Mars, right? All of those become very detailed questions, and you want to know them just not right now, you want to know them over time, right? Like, if you want to build a civilization on a planet, it has to be habitable for some period of time. How long has it been in this state? How has the planetary system evolved from its birth until now? And all of those things require knowing something about the history, the ages, the masses of the stars. And so the best case scenario we have for knowing the age of a star is our own sun, right? It is located here. We have lots of rocks where we could do radioactive dating, meteorites, rocks on the surface. We get ages to high precision. And we think the age of the solar system is something like 4.57 gigayears. So that's great. That is one data point, but it is not a generalizable data point. We don't generally get to analyze rocks from other stars. So what's the second best case scenario for stellar ages? And the second best case, like we want something that's going to be kind of similar to the sun, right? It'd be easier if it was kind of close to solar composition, kind of close to the solar age. Maybe it'd be nice if we had these stars kind of nearby to us so that we could study them well from a variety of different techniques. And it would be nice if it wasn't just one star where you only have one data point and kind of an infinite error bar, if you had a group of stars that were all born together. And the nice thing is actually that basically describes the properties of the M67 cluster. So this is a relatively nearby cluster. If you've gone out and observed the night sky, actually we observed it last night, you can see the M67 cluster as a large group of stars visible in the northern hemisphere. And if you look in the literature and say, what is the age of M67? I had a very talented REU student who went and pulled data from the past 30 years in the literature and found that M67 gets younger every year.
Yeah.
Which sounds bad, right? And if you say, okay, well, some of the old data points, you know, the error bars were large, we'll throw some of those out, you know, we'll focus on the newer stuff. Maybe you say, okay, we have about a 10% uncertainty on the age of M67 from things people have published in the past decade. But a 10% uncertainty on the second best thing we can know is a little bit concerning. Because that means that everything you're trying to do for all of the science that involves an age somewhere is stacking additional uncertainties on this 10% uncertainty. And so where is that coming from? Why don't we know the age of M67 better than that? Why can't we all agree? And the answer is usually because we don't directly measure the ages of stars. They come from some inference based on a stellar model. And so a stellar model, we make some simplifying assumptions so that we can use the physics that we understand well, put it into a set of differential equations, and figure out how a star should change over time. So we make assumptions like the star is spherical. Therefore, we can do this calculation in 1 dimension instead of 3 dimensions, which simplifies the computation immensely. We'll start with things like conservation of mass, conservation of energy, hydrostatic equilibrium, so the forces of pressure are balancing the forces of gravity, and the star is neither imploding nor exploding. There's some nuclear fusion going on, so you know the center is dense, hot, elements are fusing together, that's generating energy in the core of the star, and then we have to transport that energy through the different layers of the star to get it out. And so that gives us some idea of what the structure of a star can be and how it should evolve. And so we have built these stellar evolution modeling codes. MESA is one of them, if you've heard of that one, but there are a variety of other ones as well, where you put in a set of inputs and say, I would like to model a star of a particular mass, say 1 solar mass, a star of a particular composition, say solar composition. Is it initially rotating? No, that's too complicated. We'll turn that off. And then we put it into a modeling code which has all of these different physical assumptions and solves this set of coupled differential equations so that we can watch the star evolve in time. You start with a structure, you do some fusion, you generate some energy, you use that energy, it propagates, you change the structure because of the changes you've made to the energy and to the composition, and then you take the next time step and say, what is the new structure? And you take those steps over time to build up the evolution of the star in properties you can observe. Say the temperature of the star on the x-axis here, and its luminosity on the y-axis. So this is essentially the equivalent of an HR diagram or a Kiel diagram if you've seen those. And stars will burn hydrogen into helium in their cores on the main sequence. Then they'll evolve their structure, they'll cross the subgiant branch, they'll turn into red giants so they get more luminous and cooler, and so on as they progress through their evolution. And you can do this for 1 star, say a solar mass star, and watch how it evolves in temperature and luminosity. But then you can run models for more stars, say 0.9 and 1.1 solar masses, and watch how those evolve. And they're a little bit different in temperature and a little bit different in luminosity. And then you can do this for a whole grid of masses and look at, how the HR diagram position correlates with the stellar mass. And then if you go out and observe a star or a set of stars, you would say, well, this kind of lower middle box here is between the 1.1 solar mass line, or the 1.1 solar mass line and the 1.2 solar mass line. So probably it's about 1.15 solar masses. And each of these points on each of these lines has an age attached to them. So you can do a similar interpolation to get the age. And that's great. But when you actually when you look at these models and you try and compare them to a well-studied cluster like M67, and this is again work from Susie Byram, you look at the models, which are in green here, compared to the data points from the cluster. These are actual observations of their temperatures and surface gravities. And you find that the models don't quite match the observations to the level you would have expected. Particularly for the lowest mass stars, the luminosity doesn't quite match the model very well, and so the model spits out an age that is 10, 12, 14 gigayears old. The red giant stars similarly seem to be too hot, and so the models say that they are 1 or 2 billion years old. And those are very different numbers from the sort of 4 or 5 gigayears you get from looking at the main sequence turnoff, where these models of different ages separate really well. So generally when people are giving you an age for a cluster, they're fitting only this part of the diagram. But clearly there are some things going on where the models are not quite as good to this data as you would have expected. And again, this is supposed to be our second best case understanding of the universe. So what's going on here? So when I initially presented you the slide, I said that the modeling code has physics assumptions. And given that I'm talking to a physics department, that should have rung a lot of alarm bells, because there's a lot of things in physics that are complicated, are detailed, have uncertainties that people spend a lot of time to deal with, right? So these has physics assumptions is assuming things like nuclear reaction rates, opacities of various materials at temperatures and densities, all of radiative processes and atmospheric structure. At the top of the star, it's putting out radiation, which means you can't, assume simple conservation of energy with nothing complicated going on. We have made this one-dimensional, but this is essentially a magnetized fluid. And so we've got all of fluid dynamics. We've got what are you doing about convection, and convection in one dimension. What does that mean? You've got rotation, you've got mixing, you've got all sorts of things going on in these models that maybe, you had to make choices about to make these models exist. And different people make different choices, right? There are reasonable things you can assume that will give you slightly different predictions of how a star should evolve. So these are all one solar mass, solar composition tracks from, say, 4 different people. And if you look at that big circle there, that is the official IAU definition of the solar temperature and solar luminosity. And you ask at the solar age, which is the point on each model, which one goes through the solar properties? And the answer is none of them. Absolutely none of them go through the official IAU definition. And so that means that people are making choices in what they think the solar temperature should be, in how they parameterize the physics, in what things they want to emphasize, de-emphasize, calibrate to, that are changing the predictions of the stellar models. And it's not just the predictions of the one solar mass, solar metallicity model. You can look at these offsets in age between different models run by different reasonable people and get something like a map of how much they differ. And so the color coding here is the difference in age as a function of the temperature and luminosity of the star. So at the very, at their birth, they can be different by 100%. Somebody says they're born, somebody says they aren't, and that makes a huge difference. There are regions of the diagram where everybody sort of agrees, but there are other regions of the diagram, say up on this red giant branch here, where everybody disagrees to numbers that are worse than 50%. And that should horrify you a little bit, because if we don't know the age to 50%, at that point, I could just tell you it's 7 plus or minus 7 gigayears. Like, what have we gained? And in that initial plot, I cut off the scale and said, oh, we'll just cap it at 50%. Nobody needs to see anything worse than that. But I have a talented graduate student who's just submitted a paper where she's gone through and looked at the red giant stars specifically. And if people are trying to use ages from red giants from different models, depending on who you ask, your fractional offsets can be 90%, depending on which model grid you use. So you measure a star, you measure its temperature perfectly, you measure its luminosity perfectly, you have its composition perfectly. And if you ask 4 different people, you get a 90% different answer in what age it should be. And that's a problem. And it's a combination of the observational uncertainties, which do exist, right? The temperatures are not measured perfectly, but it's often dominated by our theoretical error estimates. Like just physical assumptions that we are making in the different models are different. And so they make different predictions of exactly where those stellar evolution tracks should run. And that gives you a dominant error source in most of these ages, especially for red giant stars. And so what's going on here? So like, we'll take one piece of physics, particularly for the red giant stars. We are assuming they have big, giant convective envelopes, but we are doing this in one dimension. So our parameterization of convection is we have a bubble in one dimension. The bubble rises some number of pressure scale heights, and then it dissipates into the background. Some number of pressure scale heights. Sounds like a really sketchy description of convection. And it's particularly important for these giants with giant convective envelopes, because it's so easy to shift the model temperature using this fudge factor that you make up randomly, pick from some model, use your solar calibration for, assume that every star convex like the sun, and you can shift your temperature of your red giant branch by 50, 100, 200, 500, 1,000 Kelvin, just changing this fudge factor that nobody has calibrated. And so that means that there's some real uncertainties in the physics that we don't understand that are no longer something we can sweep under the rug, but are really compromising our ability to measure the ages of stars well.
Can I interrupt with an anecdote?
Yes.
Oh, I remember when I was a young scientist, I went to a conference, and the conference contained Italians.
Mm-hmm.
So Italians are very, very animated, and one half of the Italians wanted the alpha, which is this number of pressure scale heights, to be 1.5, and then the other half wanted it to be 2.5, and the room was chaos. To shout towards the other that no, it's 2.5, no, it's 1.5, and that's the end of the anecdote. You can continue, and I'm sorry for the interruption.
No, what I unfortunately have to tell you is we're still having the same argument because nobody has actually come up with an answer that everybody agrees on. Because it's a fudge factor, but it means something and it changes things so much. And what Leslie has found is that this fudge factor is particularly an issue if you're trying to look things up in temperature and luminosity. If you know the stellar mass and composition of the star, then you know which track you're on. And at that point, the ages between the different model grids become extremely consistent. But if you only have spectroscopy or you only have photometry, you'll have a huge model-to-model difference like this in the inferred age. But then you ask, how do you get stars where you know the mass and you know the composition? Composition comes from spectroscopy. You take a spectrum. That's fine. We all agree on that. Estimating a stellar mass for a star is usually really hard. Maybe you have a very well characterized double-line binary. You watch the stars, 2 stars go around each other. You solve the orbit, Kepler's laws, all of that. If you're clever, you might be able to use like a single-lined binary and some extra information about the system to figure it out. Astrometry and now all of the information about how stars move that's coming out of the Gaia satellite will also map out an orbit for a binary. And so sometimes, again, if you're willing to wait a while and work really hard, you can pull out a mass from that. But unfortunately, those are things that are not generalizable to any random star in the sky that doesn't necessarily have a binary companion in a useful orbit. And so one of the tools we've been using a lot recently, especially for red giant stars, is called astroseismology. And the idea of astroseismology is that, like a shaken string or a beaten drumhead, a star will have particular frequencies at which it resonates that depend on its size and structure. And so if you look at a star for a long period of time, you take an image every 30 minutes for periods of days, weeks, months, years, and NASA has launched missions that actually do this. Mostly they're designed for exoplanets. They're waiting for an exoplanet to go in front of the star. But to do that, they have to take pictures of the stars every 30 minutes. And so we can watch the stars change. And the first big mission like this that NASA launched was called Kepler. And it looked at a particular set of the galaxy, a little bit out of the plane of the disk and kind of along the solar annulus. So at similar radii from the galactic center as the sun. They take photos of these stars over time. You make a light curve of how the star varies over time. It's going in and out, sloshing back and forth, getting brighter and fainter. And so that variation in these light curves is not in fact noise, but it is signal. And if you take a Fourier transform of the variation, look at the power as a function of frequency. At high frequencies, you see the effects of instrumental noise from the spacecraft. At low frequencies, you see the kind of boiling and bubbling from convection on the surface of the star. But in between, you see this characteristic peak of the stellar oscillation modes. And if you kind of zoom in on those oscillation modes, they have kind of like a characteristic frequency that scales as the surface gravity of the star. And if you kind of squint at them, you start to notice that there's like some regular spacing, kind of a picket fence of modes going on. And those spacings are related to the mean density of the star. So now you have something that goes as m over r cubed and something that goes as m over r squared, and you can put them together to back out a mass and a radius from a random isolated giant you have studied this way, even if it doesn't have a binary companion. And so people have done this. They've done this for thousands of stars in the Kepler field, estimated their masses. We've got spectra to get the compositions. You put them in a stellar model, and you can map out the distribution of ages of the red giants in the Kepler field. You see a peak at kind of young ages and maybe the solar age, which makes sense because we're looking at kind of solar-like stars. If you focus on stars with high alpha enhancement, so those are those elements coming from type 2 supernovae early in the galaxy's life, those tend to be much older, 10, 12 gigayears. And so you can kind of map out the star formation history as a function of time and as a function of chemistry in this particular field. And we can do this for more than 10,000 stars. Eventually, unfortunately, the Kepler mission broke, but they came up with a clever way to use the solar wind as an extra stabilizing agent. So they looked at specific fields along the ecliptic, and that was the K2 mission. And again, that K2 data allowed us to do astroseismology of large samples of giants. In this case, we weren't pointing at just one field, we were pointing at a variety of fields around the sky. And so you could map out how the age distribution, how the chemistry distribution changed in different parts of the Milky Way galaxy. Eventually, even the K2 mission couldn't be saved anymore, but NASA launched a new mission called TESS, which had a slightly different strategy. They wanted to look at more of the sky, but for less time in each chunk. And so it does this kind of step and stare things where it stares for 30 days, then it moves, then it stares for 30 days, then it moves, then it stares for 30 days, and then it moves. But that allows us to cover a huge portion of the sky, like more than 90% in the past 7 years. And so we've been able to do this astroseismology with TESS, and I have an undergraduate who is just about to submit this paper. We're almost done. Submitted as a senior thesis yesterday, where she has mapped out ages for 100,000 stars using astroseismology from TESS. And it looks pretty similar to the Kepler distribution. There's a more young stars because Kepler was kind of out of the plane of the disk, and so now we're able to pick up those younger stars that weren't in the Kepler field. But we also see this tail down to larger ages, and so on. And these larger samples are allowing us to ask questions in more detail. It's not just when did stars form in general, and we're like, oh, the stars near the sun formed approximately 1 solar age ago. But we're starting to look in more detail at particular things that are interesting. So if you're interested in like the galactic history of the Milky Way, or you're trying to connect to these giant JWST galaxies that have formed a ton of stars very early in the universe, you want to know what is up with the earliest star formation in the Milky Way. Those oldest stars, those stars that don't have a lot of metals, that maybe are enhanced in these core collapse supernova elements. what are their ages distribution? When did the Milky Way start forming stars? Was it the beginning of the universe, 13.8 billion years ago? Was it 10 billion years ago? So kind of after the peak of cosmic star formation. And with things like the K2 and the TESS data, we're starting to be able to get a better estimate of the masses and ages for the oldest stars in the Milky Way. And we're seeing things that are kind of consistent with the Milky Way forming stars as early as 12 or 14 billion years ago. And we've been able to do that with K2. And I had a graduate student here who submitted a paper where we did it with TESS as well, really focusing on those kind of oldest metal poor stars, trying to look at the ages. And when we look at the distribution of chemistry in the Milky Way, so the y-axis here is an alpha element, magnesium in this case, which is things formed in type 2 supernovae. And the x-axis is the metallicity, in general, the iron content of the stars. And you can see that there may be some difference in age between these two groups that have different chemistry. And so that's telling us something about the star formation and the chemical evolution of the Milky Way in a new way, which is exciting. And so we can look at, those oldest stars. When did they form? 10, 12, 14 billion years ago? We have some interesting stars that look like they're young, but they have the chemistry of old stars. So we think that that is telling us about stellar mergers, right? We used to have two 1 solar mass stars that have merged together, and now they are a 2 solar mass star. So normally you would guess that that star is young, but actually it is not young. It is just the effects of binary interactions over time. And there seem to be more binary interactions in these metal poor oldest stars in the universe, which makes it harder to do these estimates of what star formation was like at old ages, but also means that it probably tells us something really interesting about how stars and gas and evolution happened in the Milky Way at the oldest ages. Unfortunately, they will not let me do astroseismology for every star in the sky. It's extremely expensive. You have to stare at it for days, weeks, months, years with a very expensive space telescope. And so we have to come up with other ways to be able to get ages for these stars. And for the red giants, we are actually helped by the fact that their chemistry changes on the red giant branch. So when they are turning into a red giant, their convective envelope is getting deeper and deeper than it's ever been before. And it eventually gets into a region that was processed by nuclear burning on the main sequence. And at that point, it dredges up nitrogen-rich material from the stellar interior. And how much it dredges up, how deep, how much burning there was on the main sequence, all of that depends on the mass and the age of the star. And so when you look at a stellar model, you say, okay, well, this relationship between the carbon in the star and the nitrogen at the surface should depend on the age and the mass of the star. And when we look in the data, it does in fact do that. And so we've been able to work to calibrate how the chemistry of the star, which we can measure from a spectrum, should correlate with its age. And so you can do that with the astroseismic samples. You can do that in open clusters. So this is work from Taylor Spoo, where basically you map out, okay, given this chemical ratio, how old is my star? And that's great. Now you have there are some uncertainties to it, but if you take a spectrum, you have an age. And it works pretty well compared to what we're getting from the astroseismology. And one of the things you might be thinking is, well, okay, you have some relationship between the chemistry of the star and like its temperature and its metallicity and its luminosity and its age. That sounds like one of those problems that machine learning would be very effective for. You have some sample where you've trained the right answer and a whole bunch of stars where you want to learn what the age is. And so people have done a lot of work with various different machine learning techniques to use label transfer to go from the stars where we have something like an astroseismic age to be able to predict ages for large numbers of stars across the galaxy. And so this is a plot from Alexander Stone Martinez's paper, which is submitted, I think, which is submitted at this point, where you can see that the youngest stars in the galaxy tend to lie in kind of the disk of the galaxy. That makes sense, right? The Milky Way is one of those spiral galaxies. The young stars, the blue stars, tend to be in the disk of the galaxy. And so it makes sense that those youngest stars kind of lie along that plane of the disk. You can see flaring in the disk. You can see that there are old stars that are in kind of more halo-like orbits, more spherical orbits around, not quite so contained to that disk. You see that in the center of our galaxy and kind of the galactic bulge and galactic bar, we have populations of both young and old stars in the Milky Way, which is interesting and allows us to kind of piece together the history. But if you've ever done any machine learning, you've probably noticed that there are certain things you have to be very careful about in machine learning. And that includes things like underfitting or overfitting your data. If you tell it to fit things and you let it keep fitting forever, it will create a very specific polynomial that fits exactly the data that you gave it and nothing else. And so you have to be careful about how you do this. You also have to be careful about what you use as the training set, because machine learning it cannot extrapolate to things that it hasn't seen before well. And so if you give it a training set that has no old stars, it will decide that no old stars exist anywhere. And so I did a project with one of my undergraduate classes actually a couple of years ago, where I had them train different models using different hyperparameters. And what you could see is you could reproduce all of these issues in understanding how to transfer labels from the seismic ages to, ages from spectroscopy that will arise. And the things that they found, the sensitivity to the training data, the risk of over or underfitting, are all things that we have seen in real analyses, real attempts from people to map from chemistry and the seismic ages to the chemical ages using some sort of machine learning. And one of the things you will notice is a lot of times they will make a plot that says, what is the age that they get out of their network versus the age that they put in. And there are often trends, and there are often issues at the oldest ages and the youngest ages. And that's just a feature of how machine learning works. But it means you have to be careful. But if you are doing ages for red giants, you can get ages from things like astroseismology, which can be extremely precise and accurate. You can use things like mixing diagnostics to get an estimate of the age, and you can use machine learning that's been trained on all of those things. But what about stars that aren't giants? Because there are many people who care about stars that are not red giants. If you go back to this plot of how the models differ from each other, you'll notice there's kind of a circle in the middle where all the models kind of agree and the age offsets are less than 10%. That's a great regime, because in that regime, the 1 gig-year-old models are very different from the 13 gig-year models. And so if you have a luminosity and you have a temperature, you can estimate an age just from that to better than 20% for some of these subgiant stars. And people have done this using the Gaia data, which gives you exquisite luminosities and exquisite temperatures for hundreds of thousands of subgiants, and mapped out what the age evolution of the nearby galaxy looks like using those. You can also do seismology for some of these subgiants. And so I had a postbac student who submitted a paper where we did astroseismology using tests for some of these stars that are kind of in this regime, in this effective temperature and luminosity range, to try to understand how does the astroseismology compare to what we're getting from the models. And in general, we were pretty close. If you take a star where you measure the mass, you measure the composition, you have the surface gravity, and you look up what temperature the model says it should be, you're generally close to like 100 Kelvin or something, which is pretty close to the usual uncertainty on the temperature anyway. And it doesn't really matter what model you're using, they all kind of agree with each other in this regime. So that's a really good sign for being able to use either astroseismology or stellar models to get ages for the subgiant stars. So that's good, that's giants and that's subgiants, but what if you're a person who cares about exoplanets? Because the exoplanets are usually around main sequence dwarf stars. And unfortunately, seismology in the low mass dwarf stars is really, really hard. The oscillations get smaller and faster as the star gets smaller, which means they're going to be lower signal to noise, lower amplitude, maybe impossible to detect. So you can't do it that way. So how do you estimate ages for those main sequence stars? And one of the tools we've been able to use is how those stars rotate. It turns out the rotation of the stars slows down over time as they get older. And so you can look at the precision you get from using the stellar models and isochrones versus the precision you get for rotation. And if you're looking for looking at a low mass main sequence star, the correct answer is to use rotation, because the models just don't move in that regime by more than a handful of Kelvin over the age of the universe. And so the way the rotation-based ages work is that we know that stars rotate. And as they rotate, that changes what we observe, right? If you have a spot on the star coming in and out of view as it goes around, you can watch it get brighter and fainter and map out what the period of rotation is. Like the sun, those stars will have stellar winds that will carry away mass and carry away angular momentum, which means that the star will slow down as it over time. And if you have a couple of data points where you know the age from some other method, maybe they're in clusters or you have other information, you can map out how the rotation changes over time. And you can calibrate this using stars that you know. And so people have put together a large sample of stars in open clusters where all the stars in the cluster should be the same age. And we can measure the rotation period of each star as a function of temperature. And you see a very clear pattern where the stars slow down over time. And so if you have a star in the field that you want to know the age from, and you measure that it is 5,500 Kelvin and has a period of 15 days, it is between the green dots and the red dots. So it is somewhere between 1 and 2.5 gigayears. And so you can map this out. You find where on the plot you are, and you can estimate the ages from the rotation. It's called gyrochronology. And when you do this, you get the same sort of patterns of stellar evolution and chemical evolution as a function of time in the galaxy as you would get from any of the other methods, astroseismology, model comparison, etc. So that's great. That validates that this technique works. But if you look at this plot in more detail, you'll start to notice that it's not simple. It's not like each line is very simply, 0.1 above the next line, or that there's some change. There's a lot of regions where weird things look like they're happening. That's unfortunate because it means you need data to calibrate, and you cannot extrapolate the relation, you can only interpolate it. You also have to watch out for stars that are in binary systems, because if you have two stars close together that are tidally interacting, those tides will transfer angular momentum between the two stars and will change the rotation rate. And so if you have a close binary system, you cannot use gyrochronology in the same way. But for stars that don't have any of those problems, you can estimate tens of thousands of rotation periods from missions like Kepler and TESS, where they're taking the images anyway, getting the rotation periods, and allowing you to estimate an age. And we're hoping on the new NASA Roman mission, because it is also going to be doing photometry of very large samples of stars, that we're going to actually be able to detect something like hundreds of thousands of rotation periods with the Roman mission. And because of that, we're going to be able to estimate ages for large numbers of stars in Roman, especially towards the galactic bulge, where we really want to know, like, that formed early on in the Milky Way's history, and it's been the densest and the fastest star formation. How has it changed over time? And what does that tell us about other types of galaxies or other parts of galaxies that form stars really fast? So we're pretty excited about that future. And it means that we have a whole bunch of options for different types of stars to get ages from a variety of different methods. I think I have a few minutes left. So I'd like to tell you that even though we have these ages for a large number of regions, and even though you have to be careful because they're not directly measured, so they have uncertainties, you have to understand where the ages are coming from. And I do want to warn you that depending on where your ages are coming from and how the tools you're using are calibrated, you have to be careful with them. I also want to say that we are working hard to make better age estimation tools. Because, I have told you about a whole bunch of ways we can get ages to some level of precision at various different methods. But it would be great if we could get you better ages that don't suffer from 10, 20, 30% systematics from different models that we don't know the answer to. So for different types of stars, we're thinking about where the observational uncertainties are dominant. Can we get better observations? As well as where places where the theoretical error dominates, instead of just assuming that all models are equally good and nobody can say which one is right, can we figure out which one is better in that regime and tell you to use that model so you can get an age from that model, which was more likely to be correct? And then can we calibrate, cross-calibrate all of these different methods from getting ages to get all of those ages on one continuous scale so that you can compare ages for dwarfs from gyrochronology to ages for giants from astroseismology to ages for subgiants from isochrone fitting, and assume that all of those ages are coherent and can be compared. And so on the observational side, one of the projects that I'm involved in is called Landolt. It was one of the recently selected Pioneers class missions, and our goal is to calibrate the actual fluxes and actual luminosities of stars, because we are very good at measuring which star is brighter if you put two stars next to each other. We are actually really bad at measuring how bright in total they actually are, because you don't have a calibration source. And so the goal of the Landolt mission is to put a box of lasers in space, shine them down next to a star we want to calibrate, and then you look at how bright the laser is, which is a number you know from the spacecraft, versus how bright the star is, how many counts you're getting on your detector. And now suddenly you don't just have a relative brightness, you have an absolute brightness. And so we're hoping to get more stars where we have absolute fluxes, absolute luminosities, better temperatures, better radii, and be able to calibrate these models better. We're also thinking about systems like eclipsing binaries, which is a very classic way of looking at what are the properties of stars. If you have two stars that were born together out of the same gas at the same time, they are separate, they have never talked to each other, but they should better darn come out the same age in your model. You can take a set of well-characterized eclipsing binaries, in this case this is AIFE, and look at one is a giant, one is a dwarf. If you force the models to go through the giant, do they go through the dwarf at the same age? And the answer is horrifyingly no. And so that tells you there's something about these models that has to change a little bit to make them match. Similarly, people are looking at clusters. This is some work coming out of the Dartmouth group, Martin Ying, who has looked at running a whole bunch of models and changing all of those physics parameters that I told you about earlier. What happens if you change the mixing rate? What happens if you change the specific nuclear reaction rates that matter? What happens if you change the opacities? What happens if you account for all of your observational uncertainties? How much does the age of your cluster change? And when you do that, you find that if you do these things carefully, you can benchmark the cluster ages to something like 5%. So there shouldn't be a 10% age uncertainty for M67. We should do the work to bring that down to 5%. And even we have tried to see if there are places you can cross compare, because we have astroseismology, we have stars in clusters. What about seismology of red giant stars in clusters? How do we get the same ages from the astroseismology that we get from the cluster analysis? And again, the answer is sort of yes, but kind of not as well as we thought we were doing. And so now that we have that sort of data, we need to go back and look at it kind of as a coherent system and say, okay, is the seismology on the same scale as the clusters? Do we need to do a calibration? Do we need to check how we're doing this? And maybe, we need to make some tweaks to how we're doing the data analysis itself. Can we figure out how to match these age scales together? And there are also cases where you have binary stars in clusters, where again, you have some independent information about the two stars in the binaries. You should be able to match them up to a model, but that model should also match all of the other stars in the cluster. And what physics uncertainties are contributing to your inability to match those two things together. And so, we're trying to work all of these different directions in hopes that we can calibrate the models together and put them into a system where you can get better ages for large samples of stars and stellar populations. Because if you're thinking about this in kind of the galactic context that I introduced it, you don't just have individual stars that you would like the ages for, you would like ages for stars in a population. So you want to take models that have been calibrated by someone who has looked at the clusters and the binaries and the astroseismology and just given you models that are right. And then you want to be able to map those to empirical data for a star, given a model that is right. And so if you calibrate those models, you can actually map out what luminosity and what temperature a star of that mass and age should be, and be able to use that to get ages for stars, not only in our own Milky Way, but also in nearby galaxies. So this is work by Josh Povich, who's looked at the LMC. And you can see the same sort of age gradients in the LMC that we expect from the Milky Way, where we started forming at the inside and then we're forming out, star formation is proceeding outward over time. Similarly, once you have those models, you say, okay, a star of this age and this, evolutionary state and this mass has this luminosity and this temperature, you can go out and take spectra of stars that have that luminosity and temperature and put them together into some empirical library of what the stars should look like. And then you take those all and you put them together from these empirical templates calibrated to match the models at the right places. You stack them all into a stellar population to see what a population of stars at a particular age and composition should look like, and put together a spectrum of what a population of stars in a galaxy that is old versus young should look like. And be able to take some spectral data, integrated light, individual stars, whatever that is, and hopefully put it together into a better picture of not only how individual stars formed, but also how galaxies form and evolve over time. So hopefully I've convinced you that stellar ages are useful to a wide variety of people, but that we need to consider how precise and how accurate they actually are, because they aren't directly measured. And at some point, people started thinking that we didn't need to account for all of the age uncertainties anymore. But really, now that the data is so much better, often those model uncertainties are significant. And really, depending on what you're doing with these ages, whatever tools you're using, you should check their calibration and their methods in the region that represents the stars that you care about, in order to actually use them at the level of precision you want to answer the other science questions that are underlying these requests. And our hope is to be, we're working towards making better age estimation tools that everybody can use. So I'm going to stop there and ask if there are any questions.
Yeah, questions. I have a comment, which is, if you're going to name a mission to get a 0 point for flux and call it the Landolt mission, that's a great name. Arlo Landolt was the pioneer of high precision astrometry. That sort of thing. Photometry is what I want. That's the word I want for stars. So Landolt, great name. Question?
Yeah. That was a great talk. I wanted to know, how do you calculate the effective temperature, or how does the rotation vary with the effective temperature, or the other way around?
Right. Okay. So rotation and effective temperature have a complicated relationship, because the 0th order is that the effective temperature of the star is not changing very much over the course of its life, but the rotation rate is. And so you can make a map between effective temperature, where you can think of stars evolving almost vertically on this plot, as a function of rotation. But actually, they don't quite stay the same temperature. So these lines are actually kind of curves that you have to be careful about. And if you're in the edge where you're really rapidly rotating and have spots, those spots have a different temperature than the star itself. And so now your star is not one temperature, it is in fact 2 temperatures. And so your effective temperature is some combination of the spot temperature plus the unspotted photosphere temperature, which depends on how many spots you have and what your wavelength you're looking in. So it is not a simple, like the 0th order is you assume that the temperature tells you something about what type of star you're looking at, and the rotation period is the thing that's changing over time. But in reality, of course, it's a little bit more complicated than that.
Slightly off topic, but it did appear in a couple of your graphs that the dwarfs, like half of a solar mass or so, are quite a problem, because the actual stars, if I've got the sense of this right, the actual stars are larger than what the models predict.
Yep.
And so yeah, give me a summary. I think that like half of people think it's magnetic fields, that might not be the answer.
Right. So yes, this has been a long-standing issue, and you're right. The stars that we physically observe tend to be bigger than what we predict in the models. Some of that is the models in this regime are poorly calibrated, and everybody who actually does stars in that regime has stopped using them because they're so bad. But some of it also seems to be, like you said, something interesting physically happening. Because it's true that stars, a lot of the stars where we actually measure the masses and radii are things in close binaries, at which point they're tidally interacting, they're strongly magnetic, they're rapidly rotating, and all of those things you think should serve to inflate the star a little bit. So like some of that is definitely happening, but also we're starting to push now to kind of wider and wider systems where they're not quite as active, quite as magnetic, quite as rapidly rotating, and they still seem to be inflated, which I think is telling us that I think spots are part of it, and spots and magnetic fields of inflating the stars is part of it, but I think there's something else going on with our calibration. I don't know if it's convection. I don't know if it's something about the system of those stars. It seems to happen both for the fully convective ones and the partially convective ones, but maybe not the same quite in each domain. And like figuring out exactly what it's linked to, I think is still a big open question, because those models, as you say, are probably the massive star models are horrible and the lowest mass stars models are horrible. And both of those have to be fixed.
Yeah, the solar ones are actually okay.
Yeah, those are the best ones. So we started there.
Yeah, one more.
So is MESA still a widely used model for calculating stellar models?
Absolutely. And some of those tracks that I showed you come out of the MESA code. Most of the codes work similarly. So if you keep the physics the same, like you make the same physical choices, your model in MESA or DCEP or YREC or GARSTAC or any of the other stellar parsec, any of the other stellar evolution codes, they tend to agree. So it's really the physics choices in most cases that are changing the offsets between the different grids. It's not that the codes do work a little bit differently, but not significantly for most of the regimes that I've showed you.
I'm glad you checked that. It's good news. All right, well, that's it. Thank you so much. I thought that was very informative. Thank you.
Yeah, thank you so much for having me. I really appreciate it.
Yeah, I hope that's a